So the next thing we're going to end up introducing is rotational kinematics. So we ended up talking about the new variables for rotation last time. We had an angle instead of distance, angular velocity, and there's also angular acceleration. And in order to complete this idea, we had your arc length will equal your radius times your angle, so we've already done that. We had your speed will equal your radius times the angular velocity, at least the magnitude of the angular velocity. And so then if we take my radius times my angular acceleration, by analogy you'll expect it to be acceleration, and it is acceleration, but it's acceleration that's a little bit different from what we've talked about before. Because remember, if something moves in a circle, right, that it will end up having centripetal acceleration toward the center. Remember, that's true if it's moving, whether it's moving at a constant speed. It turns out it's true if it's constant speed or not. The formula for v squared over r will end up working even if it's not. Now, the other formula we had, 4 pi squared r over t squared, that will not work. Excuse me for the cell phone. That will not work because that there's no definition for a period anymore, because if it's speeding up, so it's getting faster, then how much time it takes to go around one circle is changing. So there's no definition for that t. But v squared over r still works. But that's acceleration toward the center of the circle. Remember, whenever you have something that's moving in one direction, if your velocity and your acceleration are in the same direction, it will speed up, right? We remember that. Velocity is in one direction, acceleration is the opposite. In that situation, then it will slow down, right? So they're in opposite directions. So in this situation, where you got an object moving in a circle, it will end up having, in general, two components. If it moves in a circle, it always has centripetal acceleration, whether it's speeding up, slowing down, or staying the same speed. But what will also be the case is, if it's speeding up, then the direction of your velocity, if you remember from the lab we had, the velocity will be tangent to the circle, right? You remember where if it was coming up like this, it will be the direction that you'd end up getting where it would come off at tangent to the surface. That if you're speeding up, then you'll have an acceleration that's going the same direction as your velocity. That's certainly not toward the center. In fact, it's perpendicular to the center. This type of acceleration, where you're speeding up or slowing down, moving around the circle, is called tangential acceleration. So that's what that a subscript t is about. And we'll end up seeing why that's important a little bit later whenever we end up starting to talk about rotational dynamics. But for right now, that's the last one of those to look at. And so at this juncture, it's useful for us to end up stepping back a little bit. We'll end up looking at all of these new topics as we go forward. That turns out there's a lot of similarity between motion in one dimension, 2 dimensions, and rotational motion. So in order to be able to characterize these, I ended up giving you a table in your lecture notes comparing different types of variables. So position, you'd end up having x for 1D, r vector for 2D or 3D. And when I write 2D, it could be either 2 or 3, but most of the time we did it was 2 dimensions just to make our lives easier. And for rotation, your angle position is theta in terms of our units. Displacement's the change in position, so it's delta x or delta r or delta theta. For your velocity, it would be v or v vector for 1 and 2 dimensions, and your the rotation is your angular velocity omega. And for acceleration, then it was a vector, or let's see if I can draw this today. on the screen. So up there, around like that, nope, backwards. Let's see if I can go up and back down. So sort of like that. I may end up trying to draw this on a tablet thing I have later. So if you have issues understanding how to draw it. We also have some additional things. We've got inertia, and inertia was mass in terms of linear inertia, and it's a scalar quantity, so it's m for both. It's the mass in kilograms. For rotation, it's not going to be mass. The units won't work. What we get instead is we write it as an I, and we call that the moment of inertia, and we'll end up giving you some values for that a little bit later whenever we end up developing it. We also then have analogs to force, because remember what force is in Newton's second law. It's the things that cause acceleration to happen. So in 1D we would have just as an F, 2D it's F was a vector because it's a vector quantity. And for rotation, what we have is force causes acceleration. So by analogy, this thing causes angular acceleration, and the thing that causes angular acceleration is called torque. It's a lowercase tau. And then finally, for momentum, we use P. We talked about, why is it P? Well, it's just what it is. So that was for 1 and 2 dimensions, and for rotational motion, we end up writing as an L, which is angular momentum. And again, that you're not expected to know what inertia, what the moment of inertia is, torque or angular momentum yet. But one of the things that's nice about this, having those analogies, is that we can end up writing a lot of formulas using the analogy. So if the formula works with stuff you're familiar with, then if you drop all of your variables aside from time in classical mechanics is just time. So that stays the same. But we can end up rewriting our equations that we're familiar with, that we ended up having for 1 and 2 dimensional motion. We can write them for rotation almost straight away. So there's, in terms of your kinematics, it's going to be exactly identical. Your big four plus, where instead of using x's, you'll use thetas. Instead of using v's, you'll use omegas. Instead of a's, you'll use alphas. But aside from that, the units are different, but the formulas will be exactly the same. So as some examples of that, I gave you for constant velocity was delta x equals v delta t, right? That's what we've done before. So the analogy to, remember the analogy to velocity is angular velocity. So the analogy to constant linear velocity will be constant angular velocity. Constant angular velocity will be delta of whatever corresponds to x, which becomes theta. So delta theta equals omega, which is what corresponds to v. Delta theta is omega delta t. So that's how we're able to get to that equation. Moreover, I went ahead and wrote out what all of your big four equations are. But again, it's literally in the formulas. You keep time where it is. But aside from that, every time you see an x, you make it a theta. Every time you see a v, you make it an omega. Every time you see an a, you make it an alpha. So those are your big four equations. And we're going to end up using those things in the next segment.